What I want you guys to do is I should structure this so you guys can all see it best in the information. So this is effectively what we want the stack to look like, right here on slide 165. If ESP points to this type of configuration, when the return instruction happens, we'll call virtual protect. We hacked in a fake return address for it. And we'll need to set up its arguments correctly so the function actually executes right. And so if ESP points at a fake stack frame is essentially what we're setting up here, virtual protect will be called, and this is what will happen. So what I want you guys to do is look at the MSDN page for virtual protect X and figure out what these parameters should be. Now I want you to actually write them in your course notes there, because that'll help you remember everything and keep track of it. And it'll allow us to sort of craft this fake stack frame in our payload file as well. So basically, at the point where we're gaining control of EIP, where EIP equals that placeholder value in your file, we're going to change that to the address of virtual protect X. And after that, we're going to put these things in. And then after that stack pivot, ESP is going to be pointing at this fake stack frame that we have created. And virtual protect X will be called. We'll change the permissions on our shellcode to be executable, then do some other stuff, and our shellcode will execute. But I want you guys to use that MSDN page to figure out exactly what these arguments will be, because we have to hack these into our payloads. That fake stack frame exists, and all its parameters are specified completely and accurately. Now you could actually use virtual protect instead of virtual protect X. The only difference between them is virtual protect X has this additional argument, the process argument. But we're just going to stick to virtual protect X. It's what I had the slides for, but you can do it with virtual protect. The only difference is virtual protect X, we have to tell it that we want to change the memory permissions for our process. So we put a -1 there. I just go ahead and told you guys that. -1 just means use our process as a process whose page we want to modify. What is the address? Does anyone know what the address of virtual protect X is?
7C80 1A61.
Other people get something similar? All right.
Is that, if we had ASLR, that wouldn't be so easy, right?
We'll talk about that. So non-ASLR, virtual protect is going to be at the same address each time, all right? What about the return address? What should this be? Anyone know? Yep.
Should be the return address of the shellcode location.
Yep. So give me a general address for what we're going to use for that.
13FD0.
13FD, I'll just say, because it's something to change for people. Sure. All right, H process, what should this be?
-1.
And what is that in hexadecimal? What should this be? LP address.
The basis on your stack. So I put 13F000, and it gives you the low end of the stack range.
Oh, does anyone have any other suggestions? I mean, I'm leaving this up to you guys. Do you guys want to go with that? The base address of the stack?
I don't know if that's the base address of the stack. I was just
Or,
looking for the,
address on the stack?
you can give the real base
Return
address. Stack limit is 136000.
All right, so I want a consensus. Who wants What do you guys want to use for LP address? And obviously, you're welcome to choose your own parameter here. You can do it your way. I want you guys to explore this a little bit. But for the class consensus, who wants to use the absolute address of the shellcode? Raise your hand. Who wants to use the address of just a stack page, like Ford suggested? Everyone's being shy. So, okay, what did you suggest?
6000.
136000. Is that right? Everyone feel happy with that? Feel good about that number? Well, we'll see if Papa Legba likes this number too. Size? What do people want for the size?
Well, 1000 hex takes you to the end of the stack, takes you to the stack base. Stack, top and bottom.
So 1,000?
Yeah.
So you want this to be 13,6000 and this to be 1,000?
No, that's not right. Sorry, 4000. No. I'm not thinking in hex. Is that?
It should be 13F000.
So Zeno says 13F000. So we got some disagreement here, so I'll put both of them.
My initial thought was F2, because that hits our range, but then I adjusted it to the 6, because that's what the TEB says is the stack limit.
Okay, so Ford, what do you want the size to be?
F is fine. For the size 1000. 100.
All right, and Zeno, what do you want the size to be?
1000. I think he may be implying that he has a different
All right,
tab
so we
than
got-
me because he said his stack limit was something that mine wasn't, right? Mine is 140,000, right? So it's all going to depend on where your buffer is relative to your stack.
That's the stack base. The limit is the low number. What's your stack limit in your TEB?
You're right, yeah, the stack limit is 136000 and the stack base is 140000.
Well, the point is there's like a number of options you can use here. I want you to sort of explore this on your own.
The point is, Ford, are you actually going to create your buffer
new
from
protect.
there? I don't think so, based on the buffer base address.
Well,
Yeah, it depends on which. As long as I use the right number, I can't do that much hex in my head. I just wrote 14000 minus 13600.
If that's what you set
Let's
to the
program figure it
size
out.
to, then that would be better. Because right now you have written on the board size 1000.
so what do you want the size to be?
I guess 9000.
900? Okay.
No. 8000.
8?
A.
8?
One of these is to learn to do hexing.
All right, well, we're all going to learn whether or not Papa Legba likes our fixed stack frame shortly, based on what values we chose. All right, so new protect. What do you guys want for this?
X40.
X40, huh?
Read, write, execute.
Okay. Old protect.
There should be a pointer somewhere in your stack. Can't be known.
Okay.
I set it to 1 byte, 1 word before my return address.
Interesting. So a lot of people can choose their own stack address there. So what I want you guys to do, and we'll break for lunch here in a minute, but I'll want to introduce the lab for you before we take off in case that people want to work through lunch. So after the stack pivot occurs, ESP is pointing right here. So essentially we want to construct a fake stack frame in our payload for the virtual protect call that looks like this. So essentially where EIP is pointing when you gain control, so where in your file where you found where EIP is being taken hold of, where you got that placeholder value, you should put your fake stack frame. And then when the return happens, instead of executing your placeholder value like AAA or whatever you put there, it's going to execute virtual protect, and this is going to be the stack frame that it's considering, for all of its parameters that are passed to it. And if you set this up correctly, virtual protect will be called, the permissions will be changed, and you'll return to your shellcode.
That worked.
Huh?
That worked.
Oh, you got it to work?
Yeah.
Joe? Anyone else get it to work?
Let Playwriter do all of it for me.
Okay. It'll probably take most of you a lot longer than that. Papa Legba was happy with Ford for some reason.
I sacrificed a couple dead chickens.
So, Ford, what you should do is identify, this is for you only since you got this so quickly. Consider you're in an ASLR environment, okay? What of these parameters is no good, and how will you deal with that? So what isn't good is these stack addresses, you don't know what the hell they are. Stacks haven't randomized. Virtual protect, you don't know what that is either. The only thing you know the addresses of is flash. So I'll let you think about for a while, and if you want, you can even try to construct your payload so that the only fixed addresses in your payload are addresses pointing into flash, because flash will not be randomized. And if you want help, you can look at that blog post I showed you. But you can do that even though ASLR isn't turned on. What you should do is try to make your payload file so that there are no fixed addresses except ones that are pointing into flash.
Alright, Ford, I'll race you to that because originally I was looking for a ROP gadget for that, so I've already eliminated one possibility. Point Ford for the getting a better memory range, but who can find ROP gadgets faster with Windebug?
And so you guys doing that, try to look at that blog post because it talks about how to do this in detail. I probably won't go over that too much with the class. It's pretty complicated, but if everyone really wants to and everyone gets done with the lab quickly, I can try to focus on it more.
So, Corey, so were you mentioning about the address range? So so basically I adjusted this with the address argument and then DW size argument, then it worked. So are you saying that if I put like not the page boundary, then you will not make the protect in the the virtual protect will gonna fail if I don't put it as a page range?
Yeah, so some of these parameters, virtual protect will fail if, like, I believe that size has to be page aligned, I think. I mean, you'll have to look at the MSDN page, I don't recall exactly. But if it's failing, what you should do is set a breakpoint for the virtual protect call. Make sure all the parameters look correct by looking at ESP right as the function begins executing. If they look correct, step out of the function with the GU command in Windebug, and then look at the EAX register to see if the virtual protect function is reporting itself as succeeded or failing. And if it failed, it's probably because one of these addresses isn't page aligned, or it could be that if you chose 13F000 and made your size like 2000, it will have tried to change permissions on a page that isn't mapped into memory, perhaps, if that goes beyond the limits of the stack. And that could cause the virtual protect call to fail.
Corey, do you have any reason why the 13F000 and 1000 doesn't work, though? So I that's what I used originally, and then I just changed it to use constants, and the exact same thing worked. So it seems like the virtual protect didn't like just doing that hex 1000 worth of range. Is there any reason that you can think of why that would be?
No, that should have worked. That should have worked. That's what we used in the last class. I'll have to look at that over lunch. Okay, so for like Ford and Veronica and Zeno, let's talk about what you guys are trying to accomplish. So currently, with the first payload you did, you had your stack frame look something like this. Right? So your stack frame looks something like this. Now let's talk about why this wouldn't work in an ASL environment. First of all, don't know where this is. The address of virtual protect is going to be randomized because kernel 32 is randomized. Return address, you won't know where this is. This is fine. Don't know this. You don't know what page of memory that your shellcode exists on because it's on the stack presumably, and you have no idea where the stack is located. It's going to be come in at a different base each time you restart the process. That's okay. That's just size field. That can be hard-coded. This is okay. No good. Don't know stack addresses. So essentially what you have for your stack frame in the ASLR environment is unknown virtual protect address, unknown return address, FFFFFF, you know that, unknown LP address, unknown Scott, or you know that. So this is what your stack frame will look like in the file. Probably you'll just hard code these to help identify them. Just to help try to keep everything organized in your payload file. And what you need to do to bypass ASLR is you'll have to calculate what these addresses are using recurrent-oriented programming and then write them into your stack frame before you actually arrive at your stack frame, such that when you finally are going to execute virtual protect, and ESP is pointing right at that take virtual protect stack frame before the return before the return happens. That will make EIT equal to virtual protect. This stack frame has to be completely filled out. All these unknowns have to have been calculated and written forward into that stack frame. Yep, so Zeno's pointing out a couple things that could help you. For regular virtual protect, you still have the old protect address. You could just make it point somewhere in the data region for flash, though, because that will be writable. It'll be a known location, and you honestly don't really care what the result of that old protect address is, so you don't care where it gets written. So you can make this address of data region in Flash, which will be known. What about LP address and return address? How do you guys think we should calculate those or go about figuring out what they are?
Well, the LP address we can get from the ESP.
Yeah, so you have to know what
Mask ESP, right?
what is one thing that allows us to know where our return address should be, where our general stack addresses are. We know at the time where we begin our return-oriented programming that ESP is pointing at attacker-controlled data, so that ESP is pointing in the general vicinity where LP address and return address should be equal to. So we'll have to do some math off of the current value of ESP and write it forward in memory. Okay, all right, now, so ESP, the ESP register points to, about where our return address and LP address should be, so that's how we'll calculate that and write it forward. What about virtual protect? How are we going to figure out that?
And finding the export address.
You could do that. That would be very difficult. I mean, you could definitely do that. It would require a lot of return-oriented programming. There is an easier way.
What was the question? I cheated.
Yeah, Ford cannot answer because he looked at the blog post. The question is, how do we calculate what the address of virtual protect is with our return-oriented programming payload? Zeno suggested looking at the tab and the PEB and walking that linked list, and eventually you can discover what the base address for kernel32.dll is. You could definitely do that. However, that is a lot of return-oriented programming. It's hard enough to do it in shellcode when you're, just executing x86 opcodes at will.
You can find any function that's also in that DLL that's in non-randomized and Flash that's referencing that address plus some offset.
So yeah, that's basically right. What we can do here is that if we were to look at the import address table for Flash 6, we would see that it is importing functions from kernel32.dll. Pretty much every binary does. So at the time our return-oriented programming payload begins running, there will be absolute addresses pointing into kernel32.dll located at a fixed address, namely Flash's import address table. In fact, it turns out the very first entry in the import address table for Flash 6 relevant to kernel32 points to like a get time zone information. This will allow us to know what the address of get time zone information is, which is kernel32 function. Once we have that, we can derive the address of virtual protect, because even though kernel32 has been randomized, the delta between get time zone information and virtual protect is not. So we read in what the address of get time zone information is, then add some calculated delta to it, and this will present us the value of virtual protect. And that allows you to calculate all the information that you need for that fake stack frame with return-oriented programming. ESP points at what you need approximately for the return address and for LP address. Old protect you can make point to anywhere that's writable, like K-user shared data or a data region in Flash 6. And virtual protect we can calculate by figuring out the address of some kernel32 function in Flash 6's import address table, and then adding like an offset to it, and that'll derive the address of virtual protect. And so you can accomplish all of this with these set of gadgets. I don't want you guys to read the whole blog post because it will kind of tell you how exactly you should do it, but this gives you all the tools that you need at exploitresearch.wordpress.com. And using these ROP gadgets, you can string them together in such a way that you'll derive the virtual protect address and the ESP address and write them forward into that fake stack frame with incomplete information so that when ESP finally points to the fake stack frame, all the information will have been filled out and you'll return to virtual protect with complete information and you'll be good to go. So I'm just giving you guys the gadgets since we don't really have a great way to scan for gadgets in here because I couldn't put Metasploit on the VMs because policy stuff, and unfortunately I don't have a copy of my personal gadget scanner on my business laptop. So I can just tell you that this set of gadgets is complete enough where you can accomplish what I just described. If you want to try to do it your own way, don't limit yourself to just doing it how I'm describing here. There are other ways you can do it. Like Zeno suggested, you could walk the tab in the tab and figure out kernel 32 that way. In which case, though, you'll probably have to look for other gadgets. And I guess to do that, you could use that Grudenhill Windybug script and just copy and paste the output to an editor and try to, do like a search for what you need there.
Wait. Can you get all of arithmetic with add 18?
You don't need it. You can get all of arithmetic with this add ECX, EBX minus 3FCC 3D00. So let's talk about, for you people working on the return-oriented programming, how we would put some of these gadgets together to accomplish something useful, so I can help get you started. So let's come over to the board here for a second, Bill. Here's the mostly happy scene, unfortunately. Okay, let's start off simple, guys. If we want, let's assume this right here is my payload. Okay, ESP is pointing right here in my payload. How would I construct a ROP payload such that EAX equals deadbeef?
Well, then you take gadget 1.
So gadget 1. So what would we put here? What should ESP be pointing to? Should it be pointing to the opcodes top EAX or to the address where those opcodes exist or what?
The address where those exist.
So what exactly is that?
So 100016F0.
Okay.
Go on the opposite side if you're doing your traditional convention.
So, oh, right. Yeah, sorry, I'm switching up the order that I'm doing this in. I was just doing it in the order that it would appear in the file, and kind of top to bottom, but since I've been doing my stack diagrams the other way, I'll try to do it that way. So we would have, okay, I'm just going to write pop EAX. Just know when I'm doing this, I mean the address of the gadget pop EAX. Okay? And then right here, we'd put the value that we want EAX to contain. So what would happen is, at the point where we execute our stack pivot, ESP would point here. And it would do, this actually signifies pop EAX return. It would do pop EAX. So it would pop this value right here. And then ESP would point right here. Okay, so let me think of another good example to show you guys.
Well, like, we wanted to do, say, an arbitrary addition.
Okay.
We've got gadget 7. So in order to use that, we've got to get a value into EBX that corresponds to some memory location plus 3FCC 3D00.
So yeah, let's talk about how we would do an arbitrary addition to ECX. Let's assume that ECX contains something we want, like, let's assume ECX, we've already gotten the address of get time zone information in ECX. And we want to add some offset to it, which will derive the address of virtual protect for us. How will we do that? So once again, we've executed our stack pivot or whatever ESP is currently pointing here.
See the gadgets easier on the video. Yeah. Yep. Thank you.
Increase the size. Is that what you said? Is that better?
Yeah, that's better.
Can you guys see that better, my VBcast people? Okay. And also, again, this is on WordPress or exploitresearch.wordpress.com. In case it's hard to see that those fonts and so forth.
So the last, working backwards, I guess, the last thing we want to do is number 7.
Okay, so yeah, the last thing we'll want to do is add ECX EBX minus 3FCC 3D00.
So before that, we have to load EBX with some address offset by that number.
Okay.
I mean, I have to believe.
So
that
what
there's
should my very first
fine,
ROP
like,
gadget
just
be?
add EAX plus EBX kind of things in the gadgets. Is there some? Is that not the case? Is that why you did? Like, did you do? Okay.
That's not the case. That's why we're using these bizarre ones. There might be, but the gadget scan that was run to produce this output limited itself to one instruction followed by a return. So you could expand that and allow yourself multiple instructions before a return, but then you would have to keep track of what's known as side effects and making sure none of those extra instructions between the instruction you want and the return screw up your current payload, and it gets really nasty having to keep track of all that. So all these ROP gadgets, this is the best we can do if we just look at one x86 instruction followed by a simple return. And that is absolutely the best we have. There's no other better arithmetic operations for that particular flash system. This is what return-oriented programming is all about. We've got to work with what we got. We can totally accomplish what we need to with these. We're just going to have to, go a little bit out of our way.
There's a typo on number 6. There should be an extra 0 on there. On the address.
Okay, so how are we going to do an arbitrary add to ECX?
So we have to get the target value into an address.
So we have to get the target value into an address. And what address should that be?
Something, I don't know.
What is a target region we can use as kind of like a scratch area that's definitely writable and readable?
Data area of flash.
The data area of flash. Data area of flash is going to be our little scratch workshop area.
So how do you figure out where that is?
You can put it into P
IDA.
and just look at the headers and use.
I mean, just put it in IDA and it will tell you what the where the data region is. Yeah, or PE view or any of those things, it'll tell you. Okay, so all right, I'm waiting on you guys. Well, what is our ROP payload going to be like? Arbitrary add for ECX. So first we have to get an arbitrary value into some memory address, right? Because the flash data region, let's just assume it doesn't contain that value that we need. Though it might.
Are all the moves relative to, are all the 2 memory moves relative to ECX? It looks like it.
Let's see. Well, first of all, we have to look at which gadgets allow us to write to an arbitrary memory address. So we have gadget number 5. yeah, gadget number 10, 11, and 12 also. So it looks like gadget number 5 is pretty useful for writing to an arbitrary memory address.
But the annoying thing about that is it trashes ECX.
Yeah,
It forces us to trash ECX, which we need for number 7. So we have to get it into the address and then get our other value into ECX before the addition.
Let's see, how can we do this? So first we would have to make a copy of ECX so that we don't destroy it. All right, we're playing Jenga now. This is full-on Jenga on steroids. Okay, gotta use our heads and be creative. So ECX contains the value we need. We have to store it. So we can make a copy of it with gadget number 8. Okay. So we sort of assume that we're already going to need this, so I'll go ahead and put move and I'm going to just annotate that ECX equals EAX equals, and we're going to assume like get times of information, because that's what we want to add an arbitrary value to. Let's say get times in. Make life easier for me. All right, what do you guys think next?
Well, now we need to get we need to get the delta into a memory location. So
Zeno or Ford, how do we?
oh, actually, no. We need to probably save that value, right? We're going to trash EAX along the way as well. So we need to use a 2 to get some safe address in ECX, and then use 5 to save EAX.
First of all, is my mic volume okay?
Okay, so you guys want to save EAX right now?
Okay, and then
Zeno, do you
I
agree with
wasn't
that?
really following along, but I was calculating the delta for once you want it. But
Yeah, we can hear you.
yeah,
Better
so
now.
I wasn't following along. Can't verify.
Okay, so we'll go with what Ford says then. So Ford is suggesting now EAX equals ECX, and we're assuming ECX started with the address of get time zone information. Okay? So it looks like our gadgets might clobber EAX, so Ford is suggesting that we save the value of get time zone information to some like hard-coded some address or something like that. Is that right? Okay. So you're suggesting we
Use 2.
use 2 to pop a value into ECX, so and this needs to be a memory and flash 6's data, right? So instead of actually looking at what that is, we'll just put
Data 1.
data 1, yeah.
And then number 5.
Number 5. So I'm going to keep track of what everything is over here. So at this point, ECX equals data 1. All right, now you're suggesting number 5. So move ECX EAX. So now we can say data 1 equals the address of, I'm just going to say GTZ, or get time zone, all right? All right, now what? Now one thing I want to point out is that it looks like we have just saved this value to a data area, and this value probably already exists in a data area, right? The import address table.
Sure. Do we have to
We can
compute
assume
though?
it because, like you said, we're assuming we have a
have to come
given
up- we
version
have
of
to
Flash
find it
6, and
somehow.
so static analysis to find the location of the import address table is a valid approach.
So I'm going to make a suggestion.
Yeah.
We know we can do add ECX memory address, right?
Mhm.
So and we know that the address of get time zone information is stored in a memory address, right? One that we know that's hard-coded in the import address table.
Sure.
So what we're going to do is we're going to pop the delta into ECX and add the memory address.
Mhm.
So I know I kind of like threw you guys for a loop when I went ahead and said that ECX already contains get time zone information.
Get it later.
Yeah, but we can just get it later. So
I mean, the real thing that we're trying to do here is trying to get a value and a memory address, then get the address of that plus 3FCC 3D00 and the EBX. So we can do number 7.
yes. So let's, with that in mind, let's rebuild our ROP payload, trying to do it that way.
Yeah.
Four.
Okay, so what's the first one we want to do? Okay, so what I just suggested.
Well, let's put the delta
4.
into.
Oh, so I want to basically, I think if you take EBX and you assume you want to get into EBX the address of the, no, because, yeah. Well, it doesn't really matter either way, actually. You can do it Ford's way or mine, but the point is you're going to be doing 4 in order to get the value, which is basically the import address table address plus 3FCC 3D00, so that it just cancels itself out. And then you need to get ECX will just pop out the using the delta. So I want to go with the simpler one to start with. So yeah, go with, I think that's what he said. So let's go with
So
the pop
pop-
ECX.
I'll pop ECX first, is what you guys are saying. Okay, and this is going to be
And that value is, oh yeah, the delta.
the delta in between get time zone information and virtual protect, right?
Which I currently show as 3368E.
Say that again?
3368E.
Okay. So at this point, ECX equals 3368E. It's important when you're building these raw payloads to keep track of what everything is equal to, because it's pretty easy to like say, oh, well, I can't just override ECX now because it still contains this important value for me. Remember, it's like playing Jenga. You got to keep track of where everything is. Okay, so what next, guys?
Now we need to use 4 to pop the,
Okay.
like Zeno said, what is it? The import address table?
Yep, I'm looking up the actual constant.
So this value will be equal to
Table.
basically the address of, we'll say like import address
Table.
GTZ plus
We have CC
3F blah, 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 blah. ESP ID. Okay, and now what?
Number 7.
Number 7.
Correct.
Yeah. Tom?
Can you? Okay. I was heard. So then, how we know where the base address of Flash? Probably you explained.
We know the base address of Flash because it is not ASLR.
Right. So we are trying to bypassing ASLR, but we are kind of assuming there's no ASLR. Oh, okay. That's okay. Different today. Okay, sorry.
So in this case, there's obviously no ASLR on Windows XP VMs. People were just curious about how we would do it if we wanted to bypass ASLR. So I'm just talking about the general strategy here.
Right.
But you know that Flash does not opt into ASLR, so even if we were on a Windows 764 root machine, we would know ahead of time where all these gadgets will be located because they're located in Flash, which isn't randomized.
Right.
Also importantly, Flash does not opt into safe SEH, so we could use any of these gadgets that we wanted to write out the exception handler if we wanted to.
No, is Flash relocatable? Because that would, if the loader decided that
Yeah,
is
so
occupied, you'd be.
If that cell was occupied, it could move it, but you'll just know, you would do like analysis on the program you're targeting ahead of time. You know, during this program's normal operation, Flash is located at this base address.
Okay. How does that, I mean, what happens in the case of ASLR though, that some other guy might have gotten randomized to that location and that might push Flash out of the way, or does it put the non-ASLR guys in place and then decide where to put the other guys?
I'm not sure how it.
I'm pretty sure it does it in the order that they're found in import address tables. So it's just doing, you know, the recursive search through import address tables. And so if someone else happens to get hit, you know, it's like if Flash is dynamically loaded when something like, you know, you browse to a web page and then it says, oh, look, there's Flash plugin, let me load it up. So it is going to be loaded after other stuff commonly in like the web browser sort of scenario. But I'm pretty sure there's no preference for ALSR modules versus others. There's basically just a recursive algorithm in the OS loader.
So it is possible that ASLR is something that you expect to be something that isn't ASLR.
Yeah, sure, that could happen, but this is your best bet. Sure. Usually you can make this work.
That's one of those things where if it doesn't work the first time, try again.
Yeah, I mean, you try to choose a DLL, a target that usually will get loaded early so that it gets its preferred base address.
Right.
Yeah, so, okay.
So I've got the absolute constant for that, if you want it. Depends.
Okay, so
you can write this sort of just underneath the IAT GTZ kind of thing. Yeah, it's 1009E148. And I found that by basically just going in with PEView, looking at the import address table location, and it's basically 9E148 offset from the start of the module, and PEView actually tells you anyways.
So this value is actually going to end up being 1009E148 plus 3F whatever, blah, 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 blah.
Yeah, good point.
Yeah. Don't you also need to offset that by the GTZ entry in the import address table?
No, that is actually the GTZ entry, the address that I gave.
Okay, and so this right here should be finally to add ECX, right? Mm-hmm. So and after all that, we have the address of virtual protect in a register.
And now we need to put it in the
Now you have to, at this point, you don't even know what the address of ESP is, so it's hard to write it ahead into the stack where your stack frame is. So this is just one part of this. You'll also have to, probably before this, so the only gadget that was available in Flash to really put ESP somewhere useful or do something with ESP, you could look, there were no gadgets like move EAX ESP or exchange EAX ESP or anything good like that. The best one we had was add ESI plus 3B, ESP. And so before we can calculate the address of virtual protect and write it ahead into our fake stack frame we're making, we'll have to know what the address of the stack is. And then effectively what you do is you make ECX equal to the stack frame and use gadgets like 10, 11, and 12 to write stuff into the stack frame. So I would then set EAX equal to the address of virtual protect, which we've just created. Notice we can't do that directly because there's no move ECX EAX. So
There is.
that's move
Number 8.
EAX ECX, the other way around.
Oh.
Or, yeah, so I guess that would be right. So you have move ECX EAX, so you could move the address of virtual protect into EAX. And then assuming you can then put the address of stack frame into ECX, it would allow you to write the address of virtual protect into the stack frame. And why did the screens turn blue? That's why. Okay, so here's one sort of ROP primitive that we're going to use to get the address of get virtual protect. Now, what else do we have to calculate? Really, everything else we're depending on is based on ESP, right? We've got to figure out some stuff about ESP. So ultimately, what we need is ESP in a register, I'd say, just so we have some, it's kind of available like a general purpose register for us to use. So how are we going to do that? How are we going to get the value of ESP into a register?
So we've got to use, ultimately we want to use number 9 to get into a memory address.
Yeah.
So before we can do that, we have to set ESI.
So we would do something like, so here's another kind of like mini gadget that we'll use. So pop ESI.
Not even that simple, is it? Okay, copy.
And then ESI, we'll say like a flash or data 2 or something like that, something in flash that's data reading.
And it's really, it's data 2 minus 3B.
Yeah. Yep. Okay.
And we also have to, which one is it? Oh, we got to get a 0 into that address to make sure it's.
So what we could do, what I would suggest, is we just make sure that the data region we choose to write to is already 0 during the normal operation of the program.
All right.
So
Okay.
let's just assume that. Data 2, I'll put 0 there. So then
9.
Okay, so now we've written the address, we've written the value of ESP somewhere. We're still have to get in a general purpose register.
Yeah. So in order to use 6, we have to set EBX 4.
Yep, so we got to set EBX. So probably do another pop EBX, right?
And the value would be data 2 plus 74A003A3.
Plus 74A. Blah, blah.
And you send it into Y, there are these huge offsets in the
Did anyone know the answer to that question? The reason is the ones with the goofy offsets are not intended x86 instructions. The reason, what happens is those instructions, those gadgets are actually occurred by splitting an intended instruction in half, all right? So probably for like gadget number 6, we had something like, move EBX 1123 loop, increment.
It was actually, it looks like it was a jump
Yeah.
followed by a move offset from EVP.
That's an important part of return-oriented programming. You don't actually have to return to an intended, like, compiler-emitted instruction sequence. You can split an x86 instruction in half just to get the instruction you need. And this was literally the best we could do with Flash. I know some of these gadgets are really goofy and awful, but they work, and that was the best we could come up with.
So Corey, I would kind of suggest that we let the people who are ahead chew on this for a little while, and otherwise we're just distracting the people who have.
Like information to like get started with how you do this return-oriented programming to sort of like build your payload. So Zeno and Ford, you guys have a better idea of how you would go about doing this now? Hopefully that gets you started at least. But I want to make sure everyone gets the regular depth and Windows XP mitigations bypass working before I solely focus on this, okay?